Hello, this is a toilet paper rolling lab. My name is Conrad Kaplan. I'm an AP Physics 1 student with Ms. Beckstead at Pasco County East School. This is a demonstration of my lab. First, I would present my derivation of the formula to find the ratio of the heights given any radius. Then using my specific toilet paper, I'm going to plug in and calculate the expected heights and then see if they turn out to be truthful. So we start out with the formula for the moment of inertia of the system, given the fact that it has an inner radius and outer radius. It's going to be 1/2 mr squared plus r squared, big R being this distance and little r being this distance. However, the problem is the toilet paper roll is not spinning. Its axis of rotation is not the center of mass right here. It's the side of it, because the toilet paper is being rolled from the side. So we have to use the parallel axis theorem, which is this. So when we plug in our values, this being the one from the center of the mass, and this being our new one, using, keep in mind, the large radius, since we're measuring the distance from the outside to the center mass, not the side of the hole, the size of the hole. We plug it in, we get this. So this is our moment of inertia for our rotating body. So our torque is going to be equal to our inertia times angular acceleration, which means when we plug in mg just being, the force of the toilet paper roll pushing down on it, right? Times big R, which is, the distance force is being applied of, which is just R. That should be equal to the inertia, which we calculated with the parallel axis theorem, multiplied by A over R to convert our angular acceleration given into non-angular. So I did a lot of the math not on here, did some cancellations, and it came to this. A is equal to 2g times big R squared over R squared plus little r squared plus 3 times big R squared. And so the time to fall for all that stuff for the free fall is actually very simple. It's just unit 1 kinematics of AP Physics 1, which we calculate to be this. And I'm specifying big H is the free fall height, and little h is going to be the height from which the toilet paper is going to be rotating. And there's a difference because some of the kinetic energy, some of the potential energy stored at their heights, with the free fall, it's all going into translational. With the rotational one, some of it is being distributed as rotational, so we lose some of that speed. That's why we have to compensate by having a lower height. So this is our free fall, time to fall, and this is our rolling time to fall. And keep in mind, you derive this using the x equals 1/2 at squared formula, where a is our acceleration we calculated right here. So I set these equal to each other to put our answers in terms of the quotient of big H and little h. So as square roots, obviously properties of square roots, we can just square them, cancel out the square roots. And we're left with this. Put h on this side and then divide by 2. And we are left with this. So this should be our ratio, given any radiuses. And correct me if I'm wrong, but I think this should be a dimensionless. It shouldn't matter if our answers are in centimeters or meters, because ultimately h over h is a dimensionless. I calculated the radiuses, and the big R, or rather, the big R, the diameter is 12 centimeters, which means the inner big R is going to be 0.06 meters. I also calculated the inner diameter to be around 1.5 centimeters, which means the inner radius is going to be 0.0075 meters. So plugging in my values of big R being 0.06 meters and little r being 0.0075 meters into here, we get a ratio of 1.5708. So this is a dimensionless unit, but it should give you our coefficients between the big height and the little height. To make things simple, the little one's going to be 1 meter, and the big one is going to be 1.5708 meters. And hopefully, this should, in theory, cause our paper towel rolls to drop at the same. 3, 2, 1, go. 3, 2, 1. 2, 1. Did we release? I don't think we released it at the same time.
All right.
3, 2, 1. 3, 2, 1. 3.
Remember, don't block the video.
3, 2, 1. Go. That was good.
That was good. That worked.
I think that should be good.
Okay.
All right. Thanks.
Sure.
Now, while the results were pretty close, there was obviously some errors with the data. This could be explained by things like, for example, the fact that the force of tension of the Floyd paper pulling down might not be equal to the mass times acceleration due to gravity at all times. It may oscillate, right? And that could explain some of our things. Also, most importantly, maybe we just didn't release at the same time at some of them. Some of them we did, and it turned out to be pretty good, but some of them we didn't, and that exposed a problem. Otherwise, I'd say the data is pretty consistent with the idea that that potential energy can be distributed between rotational and translational. And the thing is, if you have a rotating body distributing its potential energy, it will have to be distributed between two of them, which means the translational part is going to be less. Ultimately is why we had a big H over little h value of greater than 1, which is because the free fall one will inherently drop faster since its energy can purely be distributed in the translational form. It purely goes down like this. However, by using some of its energy being spun, the rotating one will inherently move slower compared to the free fall. And that's why we have a positive value.